We're gonna do some more C++. We've been building a process hacking toolkit. The idea is that it kind of should help me streamline some of the regular videos I make, but it's also kind of, it's an interesting set of problems to solve. Like, how do you actually interact with processes running on your system, on Windows and Linux, and then like, how do you use the tools that the operating system gives you to manipulate those and kind of do interesting things with them. We've got a process class which gives you the PID and the name, and then allows you to get all the memory regions, so all the allocated memory for that process, and then allows you to read and write those. And we did this last time on Windows, and then we started porting it over to Linux. So we've got a Linux specific version of the process implementation, and then also now we have a Windows specific one as well. And then we've got some like basic utilities which kind of help us out to do interesting things. So find all the processes for a name, or you can replace chunks of memory. Kind of just builds up on the bunch of primitives that we built, trying to build a slightly higher level functions. But yeah, today we're going to continue with the Linux porting of the functionality we already have on Windows. And okay, so let's get started. So in the Linux process file, we have an empty read and an empty write. So the idea is here is that these two functions, when implemented, will be given a memory region which defines an address, a size, and a protection level. Can we read that data from, this is from another process into ours, and then similarly, given a memory region and some data, can we write that into another process? So we're going to do something similar before, where we'll have a running process, and then we'll try and interact with that as we go along and see where we get to. Vim, and then I'm going to paste in some text. So this is just the Jabberwocky poem that we used last time, kind of keep it consistent. But this is not saved. I've not saved this. All this text just lives in the memory of the running Vim process. And then just check I've only got one running. Okay, and this is the PID, so it's 7552. So not backed by disk. This is just in memory. So we're going to try and read and write from this and interact with it. So how do you read from process memory? How do you read on Linux from the memory of another running process? I think you can use the proc sudo file system, but there's actually a syscall which helps us do that, or a Linux function called process vm read v. And the idea is this you give it a PID and then these I of x, which I'll get into in a second, and then this will basically read from that process or write from it. So that's what we're going to start to write up. I don't think there's anything particularly crazy about it. The flags argument is unused and must be set to 0. The return value returns the number of bytes written or the number of bytes read, -1 on error. It's pretty standard fare. It's also got a little example at the bottom, which we'll kind of be using. Okay, so let's start writing some code. So this is going to be very similar to the Windows one. We're going to have a vector of uint8ts, and this will be our memory that we're going to read from, and this will be the size of the region that we've requested. Done. Ship it. I might change this API at some point or extend it so you don't have to read and write full blocks or full regions, but at the moment, it's good enough for what we want to do. So we're going to create one of these IO I would if I had the right header. UEO, sysueo, one of my favorites. So hopefully that means I've got iovec, and then this will be the local one, and the base will be the address that I want to copy into, which will be mem.data, and then .iov. I don't know why it won't autocomplete len, but hey ho, mem.size. So hopefully this kind of, if it didn't make sense what the iovec was doing before, hopefully that makes sense now. It's literally just it's almost like a C++ span. It just contains a pointer and a length to where the IO operation should happen, like where it should take place, and also you can supply like a whole array of these, but I'm just going to do one because it's all we need. So the remote is going to be iv.base equals region dot address. This will not work because it will need casting, but let's just get something in there. Equals I guess it's region dot size, and then remote, and then if process VM read v impl PID, because that's the process that we want to read from, the local, and then there's one of them, and then there's going to give it remote, and then there's one of those, and then the last one is the flags, which must be 0 because that's what they told us it had to be. If this doesn't equal region dot size, so basically if this failed to read all the data that we requested, then we'll consider this an error. Runtime error, failed to read memory region. Right, let's go fix up our errors, of which there are going to be several. Everyone's favourite, we'll reinterpret cast that to a void star, which I'm just looking back at the docs of what I think this takes. Should satisfy that one. And then we are... Okay, so comparison of integers of different signs. So because this can return -1 on error, it is a signed integer and it doesn't like comparing these two. So what we'll do is we'll just static. I'm pretty sure we're not going to have such a big region that we would have to worry about overflows. So size t, I think that's what that returns. Yes, it is. Okay, cool. So that certainly compiles. I don't know if it works, but it sure does build. I can get rid of all these unused chuff now. All right, and let's do write while we're here. And then what we'll do is we'll take our sample from the Windows one where we where we tried to find some text in a running process, and we'll see if we can replace it. Okay, so time to write. So I think write is very much the same. I think in the Windows one I did this, so we'll just be good citizens and in debug check that our preconditions hold, because we cannot write more data than the region can hold. What we're saying here is that locally we want to copy the data into the data span that we've been writing, aren't we? This is the data we wish to write into the remote process, and this is where we want to write it to. Sorry, I was getting confused with what we just did. Yeah, so locally is the data that's going into the new process, and remote is where it's going to go to in that new process. So we're going to take this data and we're going to overwrite that. I think that should be data.size actually, shouldn't it? Because it might be less. And then we can do if process VM write v, then same stuff again. PID local 1 remote 1 0, and if that doesn't equal static cast size t data.size, then we'll throw std runtime error failed to write memory. Reinterpret cast from pointer to unsigned. Cast by qualifiers. Right. Okay, so I take the data that I want to write as constant, so I cannot modify it, because that makes sense. If I'm writing it to another process, then it doesn't make sense for me to modify it. However, this I suspect has to be a void star in the IOVec. Yeah. So now I've got, although this function will not modify it because it's just reading from this to write it to the other process, it just to do with the way the C API is, it expects this to be non-const. So I think what we're going to have to do is reinterpret this to a const void, which I don't think will fix it because it needs to be non-const, and then I think we're going to have to cast away the const, which is technically safe because we don't actually write to this, because this is, yeah, this local one is just the source of the data we want to write. So this was our sample Windows test case where we've looked for text within Notepad. So I've used the same text from the poem, so we're going to look for the text vorpal. So I'm going to make it no longer a wide string, and we'll replace all of them. So what this will do is this will basically say, find me a process called Vim for everyone that's named Vim, of which we've checked we only have one. Get all the memory regions, so every single block of allocated memory within that process. Find me ones that are both read and writable, and then use our utility function called replace memory, which will use internally the read and write methods we just implemented to first find and replace this text. So if I get Vim back up, so we can see here that the text appears here and here. So hopefully if this runs, and then run it, and then if I go back to terminal and then go in here, if I get this to reload, there we go. So I don't know if anyone saw that, but this has now been replaced from lowercase to uppercase in both places. So again, this process is running, it's in memory, not backed by disk. This text just exists in some internal buffer allocated by the Vim process, and we've found it and we've written it, so we've actually modified this program as it is running. I think the first thing, so basically the way we're going to do this is we're going to have to effectively write our own basic debugger in Linux, which is going to allow us to suspend the process and read the registers and, you know, muck around with what's going on there. So the first thing we're going to need is to start building out some more primitives. So I know that we're going to need to interact with threads because a process will have multiple threads. So let's see if we can extend our process class to get all the running threads. So we'll do that first, and then we can try and attach a debugger, or attach ourselves as a debugger to each of those running threads. So let's create a new file. Let's call this thread.h. Pretty standard fare at this point. So this is going to be kind of like our process class. This is going to be a live view onto a running thread within a process. I'm going to need some includes, int, and then memory. Right, so a thread is going to, and this is true for all platforms, at least all platforms we want to support, has a numerical ID called the TID, or the thread ID. Windows and Linux both have that, so we will construct our thread with a TID, and then let's just because we're going to use the pimple idiom like we did last time, we need to manually declare these, but then define them in the CP file, and then a getter for our TID. So that's going to be our interface to start with. So we're going to be able to say, hey, this TID represents this thread. Can you please store it? And then if we have to get it back, I think we'll probably extend this more in the future with other stuff, but this is a good starting point. And then because Windows and Linux will have different representations. Again, they'll all have this concept of numerical ID, but Windows will also have a handle to the thread, which we might want to store, so we'll make sure that we kind of abstract that away. So now in Linux, I will create thread.cp, and this will include our thread.h file, and then have our namespace, and then thread stud uint32t tid. I'm already missing some stuff. Define our implementation struct, which will have just for us here a uint32t tid. Back to the process, we can now include that, and what we want to do is find a way of getting all the running threads of a process. So we're going to want to do stud vector thread threads const. This is extending the interface for process to say, hey, can you get me one of these thread objects for all of your running threads? This thread doesn't represent running, you're not using this to spawn up a new thread within your running process. This represents that a thread that is already running in another process and will allow us to interact with that. So there is no shared state. In fact, every time you create a thread, you get your new implementation block, which has your own data in it. Okay, so over to process. Let's give this a go. So the way you get threads is very similar to the way you get processes, in that you use the proc file system. So Vim is running as proc 7552, right? So ls/proc/7552. If you look in here, you get loads of information about the running process. This is kind of where all this lives. Inside here, there is another directory called task, and this task has another directory for each for each thread, and this is its TID. So all we have to do is, given a PID, we just have to enumerate /proc/PID/task and get each of these, and that'll be all of our threads. We've kind of done this before. If I go to the Linux process utils, this is how we get the PIDs. Like, we enumerate /proc, and so I'm just gonna yoink this and stick this in here. So this will be our TIDs. I'll probably need to include the file system, and then std format /proc/the/thing/task. Then this will have impl PID, and then again we're going to go through each directory. We're going to loop through every element in this, and we're going to get out just the directories, and then we're going to go, what have I missed? And then we're going to go through all of these TIDs and then check that they are numeric only, and if they're numeric only, we're going to take a copy of that and then stick it back there. Vector task objects, and so if we construct that, hopefully that will work for us. No, not task. Sorry, thread. Right. Let's see if that blends. I'm semi-confident this is going to work, but let's try it. I kind of use this main file as like just a dumping ground for like testing ideas. Eventually, we'll probably write like a proper CLI, which allows us to actually drive this in a useful way. But at the moment, this is just a great place just to test stuff out. So const auto procs equals find process vim. And let's just assert that there's only one running, because this will just make life easier for us later on. Again, not worried about proper error handling here. This is just like a testing ground for us. So const auto proc equals procs.first. Okay, so let's get our running process, and now let's do for const auto thread in proc.threads, and let's do std print ln tid, and do thread.tid. So hopefully this will print out two lines for us, which were the two thread IDs that we saw in the proc file system. Nice. Okay, so we got those two. So now we need to start going into the actual interesting part, which is how do we interact with those threads? So how do you write a debugger? That's the question. For that, you need to use something called ptrace. So ptrace is the Linux supported way of debugging another process. So if you've ever used GDB or LLDB, this is what they use under the hood, and they just provide, I'm going to say nice, a comprehensive interface on top of that for actually interacting with it. Ptrace is quite complex for a function that has 4 arguments. One of them's an ID, one of them's a PID, and then 2 void pointers. That is surprisingly complex. So the ptrace system call provides a means by which one process, the tracer, may observe and control the execution of another process, the tracee, and examine and change the tracee's memory and registers. So this is what we want. So we could have actually done our read and writing memory through ptrace, but it's quite complex, and it's a lot easier just to do it via those 2 system calls that we used earlier. But we want to get the registers. That's kind of the aim for today. It's primarily used to implement breakpoint debugging and system call tracing. Again, we might expand into that later as well. So a tracee first needs to be attached to the tracer I would probably think the other way around. As the tracer, we will attach to the tracee. So in this vernacular, in this nomenclature, we are the tracer and Vim is the tracee. And we will attach ourselves to Vim and then interact with it. I'm not going to read through all of this, but there is some interesting points to point out. Attachment and subsequent commands are per thread. So in a multi-threaded process, every thread can be individually attached to by a potentially different tracer or left not attached and thus not debugged. Therefore, tracee always means one thread, never a possibly multi-threaded process. So this is why I wanted to do the thread abstraction first, is because we will need to attach ourselves to every single thread running in the process. That is the best way of writing a debugger, is just to attach ourselves to, is to be the tracer for every single running thread. So ptrace, it talks about PIDs and stuff like that, but actually PID can mean TID. I think it even explicitly says that somewhere from the last time I read this. But yeah, so we're going to start working our way through this. But basically, okay, so the first argument is the request. That is the thing that you would like ptrace to do for you. And these are all these enums, right? So trace me, peak text, peak user, poke text, blah, blah, blah. All it is loads, right? Absolutely loads. The one that we are interested today is get regs. We'll go through this a little bit later because there's actually some chuff we need to do before then. But this copy the tracee's general purpose or floating point registers. So this is how we're going to dump the registers. But right, so there is a whole load of stuff in this document. But the one we want to do first is ptrace attach. So ptrace attach the process in PID, making it a tracee of the calling process. So again, PID, TID, gonna have to do it for both. The tracee is sent a sig stop, but will not necessarily have stopped by the completion of this call. So what Linux will do is when you attach to the running process or thread, wherever we're going to attach to, it will send it a signal to say, hey, you should stop running because you are being attached to. So the idea is that the process is always stopped on attachment. However, by the time my ptrace call that we saw at the top is finished, the other process may not have received this signal and processed it. So we can't technically do anything with it until we know that it's in a stopped state. So we'll have to use wait PID, which is another syscall, to basically wait for that process to stop. And then when it is stopped, it will inform us via this wait PID call. See the attaching and detaching subsection for additional information. So we should have a quick look at that because I think it's important to get a rough idea of what we're doing. So a thread can be attached to the tracer using the call ptrace attach PID 00, which is what we'll do. Or I'm not really sure what this one is. I assume they are equivalent because it said so. So again, so a little bit of doc reading today, but I think it's kind of important to get an idea of what we're getting ourselves into. If the tracer wants this sig stop to have no effect, it needs to suppress it, but I do want it to have an effect because I do want the process to stop on attachment. Note that if other signals are concurrently sent to this thread during the attach, the tracer may see the tracee enter the signal delivery stop with other signals first. The usual practice is to re-inject these signals until sig stop is seen. So basically, what could happen is other signals could arrive at that process after I've attached. But because I'm also part of this attachment thing, I will get the first chance refusal on all those signals whilst waiting for the stop that I originally sent it. So what we're going to have to do is basically keep waiting, and then every time we get a signal, re-inject it back into the process until it finally processes the stop. That's like if you want to do this properly, and I think we should give it a go at doing it properly. You could just attach, wait for the stop, and hope for the best. But let's try and puzzle through some of this insane logic. Because the design bug here is that a ptrace attach and a concurrently delivered sig stop may race and the concurrent sig stop may be lost. So in the worst case scenario, someone else sends a stop to the process and it kind of gets in the way of us. I kind of like to design APIs that they are kind of hard to abuse and hard to make mistakes on. Because we're going to be doing a lot of stuff with like suspending processes and interacting with it, I think the way I'm going to initially design this is to have a separate debugger class that you put your process into, and then that provides a more restrictive API that only kind of works under the debugger. That's where I'm going with this. That's where I think makes sense. Let's write some code and find out. So let's go with debugger.h, class debugger, so hash include, have a debugger which takes a process, right? The idea here is that process is non-copyable, so we cannot accidentally copy a new process in here, so we will have to transfer ownership into it. So we'll effectively have to std move a process object that we already have into the debugger, which will leave that in a valid but unknown state. So the idea is then that you cannot continue interacting with that process object after you've debugged it. That's kind of my thought process. I think that makes some sense. And again, this is going to look very, very different on Windows and Linux. So let's just start straight off with the Pimpalidium, so we can make sure we can have some platform dependent state. Let's try this. So what I'm going to try and do is create the debugger, which will attach to a running process, suspend it, and then on the destructor will detach itself from it, therefore leaving the process running again. So in theory, we should be able to construct this object, put in a bit of a sleep, see that Vim is no longer responsive, and then after the program ends, it should become responsive again. I think that's the first step to this. Process, and then this will be process std move. Wait, did I add that in the header file? I did, yes. Okay. And then for the impl, we'll std make unique implementation. Give us some useful headers here. Memory, process. Right, so let's go through some of this miserable documentation. So the first thing we want to do is, the first thing we want to do is find the ptrace function. So if, for const auto thread in process dot threads, just need to build ptrace attach thread.tid equals -1, and then set also bring in format, throw std runtime error, std format failed to trace tid thread.tid. And then, right, so now it gets complex because now we need to use wait pid, which basically allows us to wait for a signal from this process we are tracing to wait for it to be stopped. Yeah, we'll basically give it a PID and then a pointer to a status code that we get out and then some options. I don't think there's anything to... And then we can use all these macros to basically say, to inspect that signal, and basically we wait for a whiff stopped. Returns true if the child process was stopped by delivery of a signal. So we need to keep going through, getting all the... processing all the signals, re-injecting them if they're not causing us to be whiff stopped, and then if we're whiff stopped, we can stop. So everyone's favorite infinite loop, because we're gonna have to keep on trucking with this one. So I've got the wait pid docs just off to the side. So I need a was status, and then if I'm gonna need some more headers. If wait pid of thread.tid, so if wait pid thread.tid was status 0 equals -1. So if we just if we straight up fail to wait, then again, like we are out of luck. So now if whiff stopped, so if we finally got our status, then breakout, we'll need to probably store it or do something with it later. Else, so now we've received a signal that is not the stopped one, and we need to make sure that the existing program is processing all these existing signals until it gets to our stopped one. So you do that with ptrace continue. So this is a restart operation, which means, well, actually, let's take a step back here. There's somewhere in the docs, I'm sure it tells you how to do this. Signal injection suppression. After signal delivery stop, so that is it's waiting for a signal, is observed by the tracer. The tracer should restart the tracee with the call ptrace restart. So it's received a signal. It has actually stopped, but it might not have stopped because we've told it to stop. We might need to forward this signal back onto it. So we do this with this call here, and there's a whole bunch of like different restart type options. You know, try to find. So, you know, it basically will tell you that, you know, this is a restarting operation, but we don't want to detach, so we don't want to use that one. You know, but restart the stopped Tracy process. So if we say you should continue, but using this signal. So if ptrace continue thread.tid 0. How do I get there? Turns the number of the signal which causes charge to stop. So then I use was_stop_sig on the was_status to get the original signal back. If that equals -1, then failed to. It should work because in the docs, when the tracer, so us, dies, it will automatically detach. So we want to do it manually, but at the moment this should work. So what we actually need to do here is keep a track of all the suspended threads. So at this point here, we have successfully suspended this thread, and then basically when we get out of scope, we want to make sure that we resume it. We could rely on the fact that, you know, when our program dies, the kernel will do it for us, but that's not us being a particularly good citizen, and it might, you know, we might want to do other stuff after the debugger goes out of scope, not just waiting for us to die. So let's quickly knock that up. So I think the best way of doing this is to use the auto release primitive we wrote like right on the first stream. So this is like a unique pointer for integral types. It allows us to give it a handle of some type and then a destructor, and then make sure it would call that destructor when it goes out of scope. So I think we can use this, right? So if I say auto release, what's the PID? Let's call it TID, uint32t, call that suspended threads, right? So what we can do here is before we break, we can place back our thread.tid, and then we give it a lambda const auto tid, and then we can do let me just check ptrace detach. So I was just looking this up here, how you detach. So this will then do ptrace detach tid, addresses ignored, data's ignored. Classic. Right. So what this basically does is we will try and suspend each thread. When we do suspend a thread, we'll keep a track of it in an auto release object such that when this goes out of scope, it will automatically detach it. So when our default created destructor is called, it will destruct the implementation, which will destruct the vector, which will destruct each individual element, which will then call the custom destructor that we've provided it, which will detach the thread. So I think this is enough machinery to kind of get this to work. The advantage of doing this is that imagine there's 100 threads, right? And we sort of go through the first 2 and it's absolutely fine. And then at the third one, we hit an error. We've already suspended 2 threads and we have to make sure that before our exception escapes, we are good citizens and we detach from those 2 that we've already got hold of. And so this will automatically do that, because it will when you throw from a constructor, it will call a destructor on all fully constructed members, which is this, because it's fully constructed by the time we get here. So this kind of gives us a little bit of safety in the fact that if anything goes wrong, we should not leave our target process like Vim in a sort of miserably half suspended okay, right, let's see if this works. So let's go back to main, let's bring in thread, and let's bring in chrono. So print those out, and then we will debugger via debugger debug std move proc. That will not work because this is const. Right, and then let's do stood this thread sleep for 10 seconds. So let's see. So we've got our vim here. So let's just delete everything in here. So I can type away. So if I run this, it's running. So if I go over to, so this is now not responsive, but I'm hoping when the program ends, assuming it does end. Ah, there you go. Okay. So it buffered up all the input and then replayed it, or the kernel buffered up all the input. So we've written a debugger. We can replace GDB now. We can attach to and suspend every single running thread. We can sleep for 10 seconds, and then when it goes out of scope, then it automatically detaches it. What I want to be able to do is get the registers for the running process. So we're going to need a registers class. So again, this is what I was talking about at the beginning. It's like how do you create an API that allows you to have different registers for different operating systems, different platforms, not different operating systems, sorry, different chipsets, but make it so that you can't, you know you're only going to get one at a time. I don't really know what the answer to that is. So I think to start with, we're just going to start off with x86 and then we'll just change it as we need to. Struct register si RDI RSP RBP RIP R8 R9 R10 R11 R12 R13 R14 R15. Right, okay, that was fun. No one thought they were going to watch me type out all the registers today, but here we are. Okay, so this is our bunch of registers. The game now is can we construct this and fill this in, and then presumably view the values. So we're going to want to be able to get the registers for a given. Sorry, words have escaped me. We want to be able to get the registers for a given thread because each thread will have its own set of registers. So we want to be able to dump those. So let's bring that across to the implementation. Go down to the bottom. Bring that in. Go debugger. Right. Okay. So let's go back to the documentation. So get reg. Copy the trace's general purpose or floating point registers respectively to the address data in the tracer. So we're going to give it one of the arguments was a void pointer. We're going to say stick the registers in there. Of course, like what's it going to give us? So see sys user for information on the format of this data. Address is ignored. Then this is my favorite part. Note that on Spark systems, that has the meaning of data and address reversed. So you have to, the data is ignored and the registers are copied to the address. So you have to, if you're on Spark, you have to make sure that you flip the arguments around. I have worked on Spark systems before. I'm not planning on porting this to Spark, so I'm just gonna ignore this for the moment because we've got bigger issues if we're suddenly running on Spark. But that's just a fun caveat for the documentation. Let's see if this gives us anything illuminating. So here we've got this struct user reg struct. So I'm gonna assume that because it's not particularly clear that this, at least on x86, is what's returned. So let's write some code. So we're going to need to include include that, and then user registruct. Okay, good. So we'll get that, and then if ptrace get regs, the given tid. It said this one was ignored, and then write that into regs. If that equals -1, then throw. Whatever, just copy it. Failed to get registers for tid. Okay, so if this all works, this will dump all the registers for this thread, which has been suspended, into this struct, and then now we should be able to just return our custom object by passing them all in. So we had rex equals regs.rex, and then RBX, RCX, RDX, RSI, RDI, RSP, RPP, RIP, R8, R9, R10, 11, 12, 13, 14, 15. All right. Now, if you thought you were done watching me type out all the registers, you are mistaken, because I'm going to give it another go now. It should, in theory, work. So what I'll do is we go through all the threads and get the TIDs, but we're not under the debugger yet. So I'm just gonna the first TID is technically the PID. Sure, I think so. Let's just dump that, and then we're gonna. Don't really need the sleep, but let's go auto regis equals dbd register. Right, so Vim's running. We're going to attach a debugger to it. We're going to dump all the registers for the main thread. All right, I'll bring that over here for anyone so everyone can see. They sure look like registers to me. I mean, RDI could certainly be one, and I know those do look like they stack addresses to me. So yeah, I think that's kind of a good place to kind of wrap this up. So what we did today was we extended out the functionality between Linux and Windows so that Linux had feature parity with Windows, so you could read and write to process memory. We then started fleshing out the start of our little mini debugger, which we'll need to use for more advanced stuff in the future. And using that debugger, we can attach to all threads of a running process, suspend them all, grab the registers for any of those running threads, and then at the end of it, we can detach, and that process can keep going along none the wiser.